This is part 2 of the gas laws. We're going to set as a goal for this class to make the following I can statement. The I can statement will be, I can solve for the value of R using various units, but especially the units that give the following two values of R, 0.082057 and 8.314. 8.314 is useful because pascals meters cubed, believe it or not, is also equal to joules. If you look at the fundamental units of this numerator, it actually turns out to be joules, and it's a useful quantity for when you're doing calculations on the work that gas can do, which you do in later courses. We're not going to explore that just yet, but you should know how to solve for the value of R. What is R? It's the gas constant, and you'll see later on when we treat of it how we get to that value. Just to recap then, pressure is a function of force over area. Anytime you want to describe pressure, you would use force over area. And in the SI unit for force and area are newtons over meters squared. So that's called, when you have newtons per meter squared, that's called Pascal. So the pressure is in units of pascals when you're using SI. It's important to be able to describe pressure because gases are compressible and can change volume due to pressure. Liquids and solids don't typically change volume with pressure, although if you apply enough pressure, even liquids and solids can do that. If you apply about 6 million pounds per square inch of pressure to water, you can reduce its volume to half. But how often do you see 6 million pounds per square inch of pressure? You only see that deep in the earth. Gases, on the other hand, will change volume readily with a change in pressure. So the SI unit for pressure is pascals. 1 atmosphere is the pressure exerted at the bottom of the ocean of air we call our atmosphere, so that's why we call it 1 atmosphere. It's expressed several other ways, all of which I encourage you to memorize. 1 atmosphere is the same as 101,325 pascals, so we see from this that the pascal is actually a very small unit. That's why they often use the kilopascal. 1 kilopascal is equal to 1,000 pascals, and the atmospheric pressure is equal to 101.325 kilopascals. It also is equivalent to the amount of pressure necessary to elevate a column of mercury 760 millimeters. This was derived as a result of Torricelli's experiments back in the, the 17th century. So they named this unit after him, the Tor. It's a shortening of his name, Torricelli. It's named in honor of the scientist who did the first experiments proving that the atmosphere exerts pressure. Finally, you can convert millimeters into inches, and if you do the conversion factor, you'll see that 760 millimeters is the same as 29.921 inches, and it's also equal to 14.7 pounds per square inch. So you see all these measures scattered, especially in old textbooks where they still use the Old English measure, but the official SI unit is to use the pascal. Here is a typical conversion factor where we convert from millimeters Hg, which is 1 atmosphere, to inches of mercury. Inches of mercury is used typically when you want to measure barometric pressure. Old barometers are scaled in inches of mercury. So we have 760 millimeters of mercury. There are 10 millimeters per centimeter. Notice I put millimeters in the denominator so I can cross out millimeters. I then convert centimeters to inches by putting the conversion factor from inches to centimeters, 1 inch per every 2.54 centimeters, and the final result when you feed it to the calculator is 29.92 inches of mercury. I taught you in the last lecture that there are 2 equations that we can use. It's actually 1 equation, but one is for when you have an initial set of conditions and a final set of conditions, and this equation, P equals nRT, is used when you have only 1 set of conditions and you want to measure the pressure of a gas or its volume. The symbol R is used to make sure that all the units work out together. Whenever you use a bunch of units together, you have to have some kind of proportionality so that the units make sense. And different units will require a different value of R. That's why I talk about the 2 most popular values of R, because depending on what units you use, you'll have different values of R. These are the 2 ones I want you to be familiar with. But you should also be familiar with how to derive the value of R. So the symbol R is a constant, the value of which varies according to the units used. The definition of R is established under a set of conditions known as STP, which stands for standard temperature and pressure. So 1 atmosphere of pressure and 0 degrees Celsius, which is also 273.15 Kelvin, is standard temperature and pressure. Why do they choose this value? Probably because it's pretty easy to get 0 degrees Celsius. All you do is use ice water. If you take a bunch of ice cubes, put them in water, the temperature of the bath will be 0 degrees, because melting ice melts at 0 degrees Celsius, and the temperature will not move from 0 degrees until all the ice is melted, because of the phase change that results. And then 1 atmosphere pressure is very easy to maintain, because when we're on the Earth's surface, that's the pressure we experience. So this is standard temperature and pressure. One other idea you have to memorize is that any gas, any ideal gas that is, one mole of it will occupy this many liters. This is based on the experiments of Amedeo Avogadro. So 1 mole of any gas at 1 atmosphere pressure and 0 degrees Celsius, or 273.15 Kelvin, will occupy this volume of 22.413996 liters. Now let's derive the 2 most popular values of R using these conditions. We start with the ideal gas law. PV is equal to nRT, and we isolate for R. So PV over NT is equal to R. We then assume there's 1 mole of an ideal gas, which means that N is equal to 1, the pressure is 1 atmosphere, the volume is that many liters, just like we defined over there, and the temperature is 273.15. Remember, we have to use the absolute temperature scale when we use this formula. So we have to convert the Celsius temperature into a Kelvin temperature by adding 273.15 to it. We put in all the values, and when we calculate it, using liters and atmospheres as the units in the numerator, we come up with the value 0.082054. That's the unit of liter atmospheres. If we change the units to pascals and meters cubed, first of all, we have to convert liters into meters cubed, because that's the volume of 1 mole of any gas at STP. Again, there's that standard temperature. We get the number 8.314. And the units are pascals, meters cubed per Kelvin mole. So these are all the SI units. The interesting thing here is Pascal meters cubed is also equivalent to joules, which is important for thermodynamic calculations. You can also still get the number 8.314 if we use kilopascals and liters instead of pascals and meters cubed. Why is that? Because kilopascals is 1,000 times bigger, and liters is 1,000 times smaller. So if you multiply 2 numbers, one 1,000 times bigger and the other one 1,000 times smaller, you'll get the same number. That's why the value is the same. But then the units are kilopascal liters per Kelvin mole. Typically, when we do calculations with gases, it's more convenient to use this number for R, because it allows you to use pressure as stated in atmospheres and liters. And most people are familiar with atmospheres and liters, but that's not really an official SI unit. Incidentally, if you want to convert from this value of R to that value of R, all you have to do is multiply by 101.325 and you'll get this number.